the equation of any line is what? Passing through 2 points x0, y0, z0 and x1, y1, z1 with the direction ratios. What? x1 minus x0, y1 minus y0, z1 minus z0 or x0 minus x1, y0 minus y1, z0 minus z1. Order should be same. You have to take the difference. They are called as direction ratios represented by A, B, C. And the line equation, every point x, y, z on this line, you say x, y, z lying on that particular point. This x, y, z, if it is there on that line, satisfies the equation x minus x0 by A or x minus x1 by A is equal to y minus y0 by B is equal to y minus y1 by B is equal to z minus z0 by C is equal to z minus z1 by C. You can take x0, y0, z0 or z, x1, y1, z1. One known point, ABC are the direction ratios of that particular line. This is the line equation in three-dimensional coordinate system. I expect you to please go back and see what DRs are. What is the line equation? Because it is there anyway, right? Even if you run it quickly, three-dimensional coordinate system, the Cartesian, you have to see it actually. See it once. And we define this is a general line, which is in general not parallel to any of the reference lines. It's an oblique line. We spoke about general reference planes and the planes parallel to the reference plane. Some one variable is equal to constant. Other two variables are variables. They are independent variables on that particular plane. The plane equation is, this is important for me, that's why I'm talking about it. Whenever we talk about the plane, one thing that we give first of all is the line which is perpendicular to the plane. Let us suppose the DRs of this line are ABC, direction ratios. If you know 2 points on the line, by taking the difference between the respective coordinates in the same order for all, I get the DRs ABC. We'll say ABC, I will specify which are the direction ratios of the line perpendicular to the considered plane. There can be infinitely many planes perpendicular to the same line. I know that. But if I say that there is a point x0, y0, z0 through which the plane is passing, there can be only one plane which is perpendicular to this plane and passing to that point. We saw this equation to the plane if x, y, z are the coordinates of any point on this plane. Hey, here you can see if x coordinate is fixed, x minus x1 by A is fixed, y1 by B is anyway constant because of which y is fixed and z is fixed in the line equation. Here, x minus x0 into A using the perpendicularity condition plus y minus y0 into B plus z minus z0 into C is equal to 0 is the equation to the plane. Equation to the plane is what actually? The equation satisfied by any point xyz on the plane, which basically comes to ax plus by plus cz plus d is equal to 0. Now you can see that d is what? Minus ax naught minus by naught minus cz naught is one form of the equation to the plane. In this, you can see that b is a constant. If you put the values of x and y, z cannot take any other value other than that. You can only fix two variables. Independently vary two variables. Third variable should be such that this equation is satisfied by the variables, because of which third variable is dependent. Any two can be considered as independent variable. Third one will become dependent variable. A, B, C, D are constants for a given plane. The other form of the equation to the plane that I basically worry about is with LMN as the direction cosines of the line, cos alpha, cos beta, cos gamma, where alpha, beta, gamma are the angles made by the line with vector. Actually, it is positive x, y, and z axis. Lx plus my plus nz is equal to p is the normal form of the equation to the plane that we should know for the sake of electromagnetic waves. I told it. I want you to see it once so that we can discuss it if it is required from the beginning also. In this, what is this actually? You have the axis, x-axis, y-axis, z-axis. From the origin, you have a line vector making an angles alpha, beta, gamma with positive x, y, and z axis. I have a plane. Maybe I'll just show it like this. Perpendicular to this particular plane and at a distance of p. With cos alpha, cos beta, cos gamma as L, M, N, any point on this xyz satisfies the equation Lx plus My plus Nz is equal to P. Extremely important form for electromagnetic waves. Okay, anyway, I'll speak about it if it is required also. Now, listen carefully. Any vector in three-dimensional space will have in the resolved from three mutually perpendicular components. Any vector in Cartesian three-dimensional space is of the form Ax small ax plus Ay small ay plus Az small az. Can be the displacement vector or the position vector or the field vector. If it is position vector, coordinates of the points will come into picture. And it actually goes from one point to the other point as a vector. But it can be a field vector with these components also. I have to define what Ax, Ay, Az are. Listen carefully. In two-dimensional plane, every coordinate represents a line. Corresponding unit vector is vector of unit magnitude perpendicular to that line at that particular point in the direction of increasing value of the coordinate. Every coordinate represents a line. The corresponding unit vector is vector of unit magnitude perpendicular to that particular line in the direction of increasing value of the coordinate. Here, every coordinate represents a surface. Ax is what now? Ax is the vector of unit magnitude perpendicular to x is equal to constant plane passing through that particular point. That x is equal to constant plane passing through that point at this point is what? Away from the board. Out. If I consider the point here, x is equal to constant plane towards me is a normal. Ax. Ay is what? Perpendicular to y is equal to constant right face passing through that point in the direction of increasing y to the right. At any point. In fact, what is that coordinate? Perpendicular to the top face in the direction of increasing, that is vertical line. Wherever you go, x is towards ax is towards you, ay is to the right, az is in the upward direction. Ax is towards you always, ay is to the right, az is in the upward direction. Minus ax is away from you, minus ay is to the left, minus az is in the downward direction. Now, careful now. Whenever I go from x0, y0, z0 to x1, y1, z1 and say I want to have a vector from x0, y0, z0 to x1, y1, z1, what is it I'll do? I will start at the point, move along x-axis edge, right? From x1, x0 to x1, x0 to x1 I will move without changing y, because on any line parallel to x-axis, y and z are constants. I'm not changing them. One vector I produce, that is this vector 1. What is that? x1 minus x0 for sure into ax. Then at the tip of this vector, I will produce a vector 2 going to the right, parallel to y-axis, because of which x and z coordinates remain constant. Y changes from y0 to y1, because of which it is y1 minus y0 ay plus, at the tip of this vector, graphical addition, I will draw a vertical vector towards the final point. That is a vertical vector because of which x and y coordinates are fixed for that. Only z changes from z0 to z1, because of which it is z1 minus z0 az. Final coordinate minus initial coordinate into corresponding unit vector. Now the point is this. Any vector, new thing for us now, dl bar in this coordinate system, please here concentrate now. This is the requirement for us initially. In general, a differential vector in three-dimensional space in Cartesian coordinate system is what? At any point. Very important. DL bar is change x by dx without changing y and z dx ax. Plus second coordinate you change it dy ay plus dz az. In general, in the space, dx ax plus dy ay plus dz az is the differential vector, dl bar. dl is equal to what? I want you to concentrate. dl is mod dl bar is dl for me is, you know, because we derived it now, dx square plus dy square plus dz squared. I told you, we are there at dl. Concentrate. Any line in this three-dimensional space will have only one independent variable, I told you. In x minus x0 by a, if you fix x, randomly fix any x. Now, y minus y0 by b should be that x minus x0 by a, because of which y gets fixed. That should be equal to z minus z0 by c, because of which z is fixed. Here, only one variable is independent, x. Y is f of x. Z is g of x. Definite. Any general y is a function of general x. Any general is another function of general z. Z is another function of general x. Or you can always say f of y, y, g of y. Some other functions. It may not be f and g only. Or it can be z, f of z, g of z. Only one is independent variable. If somebody asks you to calculate the length of a curve defined in three-dimensional, any curve also, any line or any curve in three-dimensional coordinate system will have only one independent variable. In that particular case, this dl either becomes root of 1 plus dy by dx whole squared is what? F of f dash of x plus dz by dx whole squared is what? G dash of x squared into dx. dl is what? dl is this. L is what? Integral x0 to x1 of this, or integral of dx by dy whole square plus 1 plus dz by dy whole square into dx. Sorry, dy. If I want to integrate it with respect to y and get the length. Or in the same way, the extension is good for us. Dx by dz whole square, dy by dz whole square plus 1. Every term will be in the function of, in this will be function of z. dz is dl. Integrate it. If you use the first expression, use x limits. Second expression, use y limits. Third expression, use z limits. Check it. You should know. Differential surface elements. Now, these differential surface elements in any coordinate system are defined only on standard surfaces in that particular coordinate system. When you talk about differential surface element, it's on a surface. That surface in Cartesian coordinate systems cannot be sphere defined in that coordinate system, cannot be cylinder defined in that particular coordinate system, or cannot be a plane ax plus dy plus cz plus d is equal to 0 in this coordinate system, or lx plus my plus mz is equal to p. They are defined only on the standard planes. dsx is what? Differential surface element on x is equal to constant plane is equal to dy dz on x is equal to constant plane. Only y and z can change. Please understand this. dsy is dx z is on y is equal to constant plane. dsz is dx dy on z is equal to constant plane. Only these things are defined for the sake of surface area. I can talk about the surface area of a window or anything in x is equal to constant surface. You give me the shape. But not on oblique planes or curved surfaces. Okay? Proper definitions. Concentrate now, because we should know this. Whenever we talk about a plane, a surface, we invariably should give its orientation. Very important for me. Either by giving the direction ratios of its normal or the direction ratios of the line perpendicular to the plane is to be specified. Otherwise, we will not know the orientation of it. LMN, direction cosines of the line starting at origin and coming towards that particular plane. It's a vector. LMN are the directions. For the line, there are no directions actually. It extends in both. For the vector, only specific direction. In the same way, Listen carefully. There is a vector passing through a surface, vector field. I want to determine the normal component of that vector to that surface. At any point. Carefully listen. Given a surface equation, when we go to the gradient, we discuss something called as directional derivatives. We can determine the unit vector perpendicular to the surface at any given point, given a mathematical representation of the surface. This is normal vector to the surface. Then, if there is a physical quantity going in this direction, if I know theta, that into cos theta will give me the component of that physical quantity perpendicular to the surface at that particular point. Essentially, in Gauss law, we say net outward normal flux through the closed surface. Flux is three-dimensional when I want to talk about outward normal component. Normal component is what? This is actually the unit vector un cap. If this is vector v bar, what is the normal component magnitude? V bar dot an is normal component of that vector magnitude. And you integrate that normal component to say net outward normal, total outward normal component of that particular field quantity. So, whenever we want to talk about the outward normal component, for every surface, we should either give the unit vector perpendicular to the surface, or given the surface, we should use the gradient concept or directional derivatives to determine the unit vector at that particular point. There we talk about dsx bar. D bar dot ds bar is what we have to understand for the sake of vector calculus. You should not ultimately wonder what is this ds bar, what is the vector in a surface. No, dsx bar is what? It is actually dss is dy dz only. Bar because what is the normal direction to it? Whenever I am there at x is equal to constant plane at a point, dsx bar is actually a differential surface element at any point on it is dy dz. Normal direction to it is what? Plus ax or minus ax, depending upon the case, I will take. Into plus or minus ax is dsx bar. Please remember this. It says the vector normal to this ds is ax cap or minus ax cap. Next, dsy bar is dx dz plus or minus ay. I'll tell you where plus or minus ay comes into picture. dsz bar is equal to dx dy plus or minus az. No, depending upon the case, you have to take plus x or minus x and do the problem. There are some places where whether you take plus x minus x, ultimate answer is not different. Boundary conditions is the place. And boundary conditions happen to be very important. So all these critical things are to be covered before going into those topics. I'll tell you. I have some physical quantity, flux density. I know the flux density at any point. That's a general expression I know. I want to calculate the total outward normal flux through a regular surface defined in Cartesian coordinate system. Listen, d bar is known to me. It's an expression in the function as a function of x, y, z. I want to calculate the outward normal flux through this closed surface. When I talk about the right face, what is the outward normal direction? Plus AY. D bar dot plus AY talks about outward normal component to this face. ds bar here is dsy bar, which is equal to dx dz ay at any point. Ay. In the same integral, ds bar is there on this surface. What is the outward normal? For this face, outward normal is minus ay. Inward normal is ay. For the right face, outward normal is ay, inward normal is minus ay. When I want to talk about the net total outward normal flux, what is ds bar on this surface? dsy bar equal to what? dx dz minus ay. Please remember this. Depends upon the case. In the same way, on the hind face, outward normal is minus ax. In the front face, because it is coming towards you, outward normal is plus ax. Bottom face, outward normal is plus az, minus az. Top face, outward normal is plus az. At each and every face, I have to integrate. Before integrating, I should take the normal component. Outward normal component, if I want to take, means that ds bar is defined there. In fields, we introduce that quantity as integral vector bar dot ds bar. I want to understand this vector bar dot ds bar as what? Integral of v bar dot an cap, which is the required normal direction into ds. This is a constant. V bar dot product is scalar product only, definitely. Somebody, if they say v bar dot ds bar is to be evaluated, you have to write this as integral of v bar dot ds an cap normal, or an in the simple terms that we normally try to tell. You represent an is unit vector which is normal to the given surface. V bar dot ds an is what? V bar dot an is a scalar into ds. And through this only, we will talk about divergence and Gauss divergence theorem. Okay. These are differential line elements we discussed. Differential surface elements we did. Differential surface elements in the vector form or the basic scalar form are defined only on the standard surfaces in that particular coordinate system, not on the non-standard surfaces. Standard surfaces, some variable constant. That's all. Check it. Differential volume element. This is new for me, right? In a differential volume is, it's a parallelepiped, right? With mutually perpendicular edges. X, change x by dx, produce one side. Change y by dy, produce other side. Complete the rectangle. Change z by dz, height of this parallelepiped, right? This is the differential volume element, dv equal to dx, dy, dz. Very, very important thing, because we have mensuration as a topic in aptitude. We are supposed to do many volume calculations. All standard volume expressions are derived for you to become fast in actually doing things. For you to know the procedures, volumes of different standard objects, right, are taken as what? Integral of any volume is what actually? Volume integral of dv, which is either, now again, dx, dy, dz with x limits, y limits, z limits, I may change the order of integration depending upon the case. X limits can be constants or functions of y and z. Limits are constants or and by r. Functions of y and by r z. Now y limits can be constants and by r functions of z. That's all. Because once you evaluate the integral with respect to y and substitute the limits, I can have constants and z terms because I will be integrating it with respect to z. Why? After integrating it with respect to x and substituting the limits, I should not have x component. It can be a value, or the variables y and z can be there because y and z integrals are there. I'll tell you anyway. Then once I evaluate the integral with respect to y and substitute the limits, only z variable is remaining, because of which it can be constant or function of z. The z limits are always constants. In general, when I basically evaluate triple integral, carefully, integral of dx1, dx2, dx3, let us not worry about the specific names. x1 limits are either constants or functions of x2 and by r x3. x2 limits are constants or the functions of x3 only, function of x3. Ultimately, x3 should give me a constant, because of which constants only. Because I may, corresponding to a particular case, I may change the order of integration. Listen carefully. When I say I integrate it with respect to x first, carefully look at it. Integral x limits dx, dy, dz is at any y comma z, correct? X limits are put at any y comma z. Try to concentrate. Y comma z is my yz plane. Dy dz is this. I am extending it in x direction from one surface to other surface, correct? Correct. No, from constant surface or variable surface. I'm not worried about it. Carefully, what is that I get? Sorry, it's a surface only. I will get this as the volume when I basically do this x1 to x2. It is a rectangular prism, right? Or square prism. Prism, huh? Correct only? Am I right? Yeah. I will basically first consider this volume. Such prisms are considered everywhere on the xy plane to talk about the entire volume. Then such prisms along y limits, then z limits to cover the entire volume. Please check them. I want you to first of all understand, because I want to do problems on single integrals, double integrals, triple integral, looking at the applications of it. At least on alternate days, we'll discuss problems. Fields, we have to take it forward because that happens to be fundamental to many subjects. In parallel, we'll start talking about the fields fundamentals so that by the time we complete line, surface, volume integrals, we'll come to gradient, talk about the applications of gradient, or divergence, talk about the applications of divergence and then Gauss divergence theorem. We'll be learning the subject as well as mathematics, one helping the other actually.